Jerome is a PhD level mathematician with a lot of experience in development and um, like like contract work as far as he has his own contracts with the government and large companies. So he's been in this kind of AI game for a very long time too. So let me unmute him. Can you hear me, Jerome?
Yes, I can hear you. Can you hear me?
Yes. Yeah. So maybe just like
Wonderful.
5 minutes or something. That'd be great.
Yeah, I might go a little longer, but let me go if I go overboard. So, first, a little bit of my background to give you some context how I'm dealing with this. Can everyone hear me before I continue?
Yeah, I think so.
Wonderful. So, um, I'm originally from the East Coast, and when I got into this field, I was originally interested in cognitive modeling, and I, started working in this area in the 1980s, and originally as an electrical engineer, and then I switched over to computer science. I came out to Utah in 1989 and worked on my PhD in computer science while supporting myself by being a researcher for the Department of Veterans Affairs, where they deal with medical research and electronic patient records. So over that time, I went from being this idealist that wanted to make the super brain to, more of an engineer, which is, can I use these technologies and kind of minimize the hype, but understand them from an engineering standpoint, the strengths and weaknesses of different approaches, and the goal with many of these things is to try to get the simplest model that can solve the problem. Because when you build these kind of models, there's a tendency to overfit your data, and simplicity is good. Sometimes when you build a very complex model, it's difficult to understand what it's doing, and it can lead to bad effects, bad behaviors near the boundaries. So, I'm coming at this from a perspective that, yes, my PhD was related to deep learning, but um, we want to start with the most basic models in a very bottom-up approach and try to see, comparing these different kinds of models, can we get simple models that solve our problem well and as necessary move to more complex models. So that's kind of the perspective that I'm taking, is that we want to look at these things. And so when Jordan did the first model that he did, he chose a library that was based on XGB, I believe. And what we did was we took a look at what tools were out there and how can we leverage things so that a person running these tools doesn't need to be a PhD in data science, computer science, or probability theory. We want to see if we can automate many of the steps and processes that, if you look on examples on the internet, they basically do many things in a very manual way. They do a graph, a person looks at it, and then they try to create a model from that, and their assumptions are step by step with a person in the loop. And we've been trying to go through and identify things that can be automated at various steps in the process. Ways you can characterize the data that will automate decisions that allow you to make a better model, that in the past you'd have a PhD data scientist, just graphing out the data and running the stats themselves, and they didn't really link these things up into some kind of pipeline. So some of the goals of the engine from my perspective is that we want to take a set of tools that are out there. There are literally hundreds of open source libraries in Python and R and things like that, and we want to identify those that are considered to be best of breed and very standard in terms of APIs, and chain those together, integrate them, so that right now we already have working baseline forecaster for moving averages, multiple kinds of decision trees and forests, a standard time series approach called auto regressive integrated moving average, or REMA, and also some more basic deep learning models. And the idea is to make these things work together, leverage all these existing libraries that are well established, but we want something that's modular and customizable, so that probably sometime about 1 to 2 weeks from now, we'll be at a point where the equivalent of 1 to 5 lines of Python code, or the user interface to those 1 or 5 lines of Python code, will be able to run a full pipeline that integrates all kinds of capabilities, including model creation, selection of optimal input features that serve, as the inputs to the model, reducing that set, selecting the optimal hyperparameters for learning, and doing, training and test cycles, and ultimately being able to predict in the future a specified number of time steps with the intervals. So before I continue, does anyone have any questions? I'm almost done with a high level, but the goal here is that we want this suite that could be potentially running 100 different configurations automatically, going all the way from testing the previous day's performance to, building the new model and doing a forward projection where you can compare them for specific data. And although we've not implemented it, we can even build in features to do explainable AI to basically better explain the models. But the goal is, again, to get models that are as simple as possible for certain kinds of problems, and evaluate their performance over time, where you want to go with a small number of moving parts, smaller number of features, smaller number of parameters, and get something that can be explainable, robust, and understandable. And use standard tools and make it easy for a person that's not a Ph.D. to be able to use the software quickly with minimal programming or minimal interaction with a user interface or a batch process, and handle all kinds of special contingencies. Like, for example, some data sets have trends in them, and the best models would extract the trend and then model what remains. Other ones have seasonal cycles. Again, if we can take advantage of the knowledge by automatically running these statistical tests, we can then build a model that's much more robust than just throwing a black box at it. In many cases, not all cases. And we can handle things like missing data. Optimize the model to handle missing data and all kinds of different contingencies like that when a statistician or a theoretical data scientist attacks a problem, they kind of have this toolkit inside their head for the kinds of tests they run, the kind of decisions they make. And what we're doing that I haven't seen anywhere is to automate many of those decisions that the data scientists just take for granted, and make it so that they run automatically. The users can configure some preferences, and then based on those preferences and based on a library of different specialized statistical tests, it'll build out this complex model that'll be optimal for the characteristics of the data. So that's kind of the big picture. I can't do a demonstration right now because I'm doing this from my phone because of some communication issues. But basically, we already have, I think, something like 10 different classes of models working right now from begin to end. And we also have partial for some specialized libraries for deep learning. And again, with the deep learning, the emphasis even there is on modularity. So there are different tools that are out there, and we're using a higher level API known as Keras, which allows us that a person can choose their favorite deep learning backend. For example, TensorFlow or Torch, and that's abstracted away. So these are some of the kinds of issues from my perspective, is that we want a suite of libraries. They could be an ensemble, though we haven't dealt with that yet. But the important thing is to take knowledge of statistics and the structure of the data to effectively determine what the best characteristics are for the models, how to pre-process the data in different ways, what parameters to send into these things. Because if you just throw a black box at it for many of these things, you'll get a model that works but doesn't take advantage of those assumptions, and you will end up overfitting your data. So that's kind of my high level. Does anyone have any questions?
I think that's perfect, Jerome. I'm
Yeah,
really.
and the other thing, sorry, I want to say is this complements what Will is doing, because in the spectrum of deep learning, some of the LLM models and some of the things that Will is looking at try to do some of the steps that I'm automating explicitly, but within the models themselves. So it's just that in practice, it just depends on the data set. Which approach do you go with? Do you go from the top down with a kind of a set of signatures for kinds of approaches that work? Or do you go the bottom up and historically basically see which classes and models work for which data sets and learn from that, to try to capture the unique challenges of a given data set and what you're trying to accomplish? I'm sorry for cutting you off.
No, that's perfect. I mean, you're talking about how we're just automating all of these tools, and I'm surprised, like you've mentioned this a lot to me. I mean, we're both surprised that nobody's done this yet, that it hasn't been done. So and I think what we're building as far as the engine goes is really quite impressive and unique. So anyway, thank you for going over all those details, or that high level overview.